Hello everyone, how's it going? My name is Dan the Tutor. Today I wanted to look at a topic in Calc 2 with series and sequences. At this point, you've probably been doing series for a while, or at least long enough to get the hang of when things converge or diverge. I just wanted to make a quick cheat sheet to talk about 4 series about which of these series have the strongest behavior. Let me show you what I mean. You basically have 4 kinds of series that converge. One is 1 over n squared, or that can be n to any power. I'm just choosing squared. Then you have 1 over 2 to the n power, where the 2 is replaceable with any number, but the n is in the exponent. Then you have 1 over n factorial, which if you remember what factorial means, like for instance 4 factorial is 4 times 3 times 2 times 1. And then the last family we have is 1 over n to the nth power. Now all 4 of these series converge, but what you need to know is that they have a hierarchy of how strong they are. So basically, from weakest to strongest, I would say 1 over n squared is the weakest and 1 over n to the n is the strongest. And this is in the right order, by the way. It's 1 over n squared, then 1 over 2 to the n, then 1 over n factorial, and 1 over n to the n. But what do I mean by strongest? I'll tell you. Basically, if you have a series that uses 2 of these things, such as the series from n equals 1 to infinity, of let's say 2 to the n over n squared. This one uses 2 different rules, in the numerator and the denominator. And basically what I'm saying is that if you have these 2 series, we know that normally both of them would converge if they were in the denominator, but when you put them like this, I can immediately tell you whether it will converge or diverge. It depends who's stronger. In this example, 1 over 2 to the n is the stronger one, and the reason why is because on this list I just made, 1 over 2 to the n is stronger than 1 over n squared. And so because of that, I immediately know that the answer to this is going to diverge. Now this isn't enough on its own to prove it. This is not one of the series tests that we would normally use to prove that it diverges, but this is a way to at least check your answer and make sure you're on the right path. By the way, all of these series don't matter for the 2 specifically. Like for instance, I can have n equals 1 to infinity of 2 to the n over n to the 100th power, and still, even though the 100 is bigger, this is a stronger form. So again, it would diverge. And obviously if you flipped it, like if you had n to the 100 over 2 to the n, well then this would converge because now the stronger thing is in the denominator. But one question we still have is, how would I prove it? What test would I use to prove any of these things? Well, basically, here's what I would say. Let me write out the 4 terms again. 1 over n squared, 1 over 2 to the n, 1 over n factorial, and 1 over n to the n. So if you have the 1 over n squared case, you're going to want to use a limit comparison test or a normal comparison test. I prefer the limit comparison test, but a direct comparison test will work just as well. Then if you have 1 over 2 to the n, or if you have 1 over n factorial, both of these you're going to want to use the ratio test. The ratio test works great for n in the exponent or n factorial, which is both of these cases. And then for the final case, the 1 over n to the n, there's only one way that I know of to prove this, and that is the direct comparison test. And then what if you have a mixture of 2 of these? Like for instance, what if I have the example I already used, 2 to the n over n squared? Which test should I use? Should I use the ratio test or the limit comparison test? I will tell you, you use the ratio test because you always use the highest level test. Which means if I have 2 over n squared, you should use the ratio test. If, for instance, I had the series of n factorial over n to the nth power, you should use a direct comparison test because that's what I said right here. This is the strongest one. You use the strongest one. And the only time you would ever really use the limit comparison, the 1 over n squared case, is if you had some series that looked like this. This is where you would use a limit comparison test. When they're both n squared and all that stuff, that's when you would use the limit comparison test. But again, the direct comparison test would also work as well. So now let's look at some examples where we're actually going to solve these. So the first example I have, it's the series from n equals 1 to infinity of n factorial over 5 to the n. So first of all, we notice that n factorial is the stronger form, meaning that my guess is that it's going to diverge because that's in the numerator. However, the way I would prove that, since both of these use the ratio test, I would definitely use the ratio test. So if you remember, the ratio test is where you take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, where this whole thing is our a sub n, and a sub n plus 1 is the n plus 1th term, which would be like n plus 1 factorial divided by 5 to the n plus 1 power. And the absolute value doesn't even matter here because there's no negatives here. So this simplifies to limit as n goes to infinity of quantity n plus 1 factorial over 5 to the n plus 1 divided by n factorial over 5 to the n. Now personally, I don't like this because it's a complex fraction. So what you usually do with the ratio test, you usually rewrite it by multiplying by the reciprocal. And so that will look like this. N plus 1 factorial over 5 to the n plus 1 times 5 to the n over n factorial. See how we got that? We flipped the denominator and multiplied. Okay. Now the next thing you would do for the ratio test is you would break it up a little bit. You'd start simplifying. So if you want to know more about why this is true, you can go back to my video on the ratio test. But basically, I'm assuming you know this already, that n plus 1 factorial can be rewritten as quantity n plus 1 times n factorial. And the denominator, 5 to the n plus 1, can be rewritten as 5 to the n times 5 to the first power. And then still times 5 to the n over n factorial. Here's why the ratio test works great, because the n factorials cancel, the 5 to the n's cancel, and all you're left with is the limit as n goes to infinity of n plus 1 in the numerator and a 5 in the denominator. And obviously when you plug in infinity, this is going to go to infinity, and since infinity is greater than 1 for the ratio test, we would say the answer is diverge. And so that's it for that one. The next example I want to look at is the series from n equals 1 to infinity of numerator 3n squared plus 1 divided by n squared minus 6n plus 4. So once again, I'm not going to explain how to use the limit comparison test, but I'm going to use the limit comparison test. And the reason why is because this is both of these the n squared rule, which means since they both follow the n squared rule, I'm going to use the limit comparison test. So the limit comparison test says you need to compare it to a series that will act similarly to this one. Since you have n squared in the numerator and the denominator, I know this is going to act like n to the 0, which is the same thing as 1. If, for instance, I had n squared over n cubed, and then like a bunch of other junk in the numerator and denominator, then I would compare that to 1 over n. Basically, you just cancel out the leading terms, like the n squareds, until you have the most basic form. That's how we do the limit comparison test. But we're not done yet because we still have to prove it. So I would say we're comparing to just 1, the series of 1, which we know diverges. And so basically, if you take the limit as n goes to infinity of b sub n over a sub n, where b sub n is the series that we're comparing to, which is the 1, and a sub n is our original. By the way, if you wanted to, you could also do a sub n over b sub n for this limit. It does not matter. But what I have is the limit as n goes to infinity of b sub n, which is 1, divided by that whole thing, a sub n, 3n squared plus 1, divided by n squared minus 6n plus 4. Again, I have a complex fraction. I'm going to flip the denominator and multiply. That's limit as n goes to infinity of n squared minus 6n plus 4 over 3n squared plus 1. And this is just a limits at infinity question. I would say that the degrees are equal, so you actually look at the coefficients in front of them. The coefficient in front of the n squared is just a 1, and the coefficient in front of the n squared is 3, so the answer is 1/3. And the limit comparison test simply says that if you get a finite meaning not infinity, and non-zero number, so that satisfies both criteria. It's not infinity and it's not zero. Then that means that our series A sub n, the original, does whatever B sub n does. And we said that B sub n diverged, so therefore A sub n, the series we care about, will also diverge. So we confirm that this series diverges. And then the last example we have is the series from n equals 1 to infinity of n factorial over n to the nth power. So it's not obvious just by looking at this which one is stronger. And again, you can't use the ratio test because if I scroll back up to my notes, the ratio test is not going to work for 1 over n to the n. And since 1 over n to the n is the strongest form, we're going to use a direct comparison test. And here's the cool thing about the direct comparison test. I think you're going to see pretty quickly why this is going to converge. Oh yeah, and we know it converges because that one's stronger. The denominator's stronger. So we know it's going to converge. So let's just compare it to something that we know converges. For instance, I know that the series 1 over n squared converges, and this is always the easiest choice to use for the comparison test. Now you can't always use 1 over n squared, but I'll tell you it does work this time, so it's a good first try to use in the very least. And so here's what I like to say. This is my B sub n, this is my A sub n, the original. If you want to use the comparison test, the direct comparison test, to prove that this converges, then our A sub n needs to be smaller than B sub n for every term, or at least as n goes to infinity. So basically, I would say this. First, I would write out n factorial over n to the n, and I would write out the first few terms. So first we have 1. 1 factorial is 1 over 1 to the 1th power is also 1, plus 2 factorial is 2, divided by 2 to the 2nd power is 4, okay, plus 3. 3 factorial is 3 times 2, which is 6, divided by 3 cubed is 27. I'll do one more. 4 factorial is 24, and 4 to the 4th power is a number so big that I need to plug it in a calculator. 256. Actually, I changed my mind. I'm going to do even one more. 5 factorial is 120, and 5 to the 5th power is 3,125. Okay, now I will start writing out the terms for 1 over n squared. You have 1 over 1 plus 1 over 2 squared is 4 plus 3 squared is 9, 4 squared is 16, and I want to make sure I'm matching up my terms. Okay, so I'll do one more, plus 1 over 25. Now it's not obvious at first glance that the top one is smaller like we need it to be, so let's get some decimals for these just so we can have a better idea of what's going on. 1 is obviously 1, I don't even need a decimal for that. 2/4 is 0.5. 6 over 27, let me plug that in the calculator, 0.222. 24 divided by 256 is 0.09. 120 divided by 3,125 is 0.038. Now let's do the same thing for the other one. 1, 0.25, 0.111, 0.063, and 0.04. Now I know you can't see all those together, so let me draw them closer together. Okay, so again, these are the decimals we got. This was my A sub n. This was my B sub n that I was comparing to. You'll notice that this one's the same. This one's smaller, which is not good for the comparison test. This one's smaller, but hey, on the very last one, we get that that's smaller. And if you continue this trend, I promise you, if you do n to the 6th, n to the 7th, everything like that, your A sub n is going to be smaller for every term after n equals 5. I promise. And because of that, we would say A sub n is smaller than B sub n as n goes towards infinity. And so then I would say by the direct comparison test, DCT for short, my series is going to converge just like I said it would. And that's it for today. Just wanted to go over these basic rules. So one more time, the order is 1 over n squared is not as strong as 1 over 2 to the n, which is not as strong as 1 over n factorial, which is not as strong as 1 over n to the n. And then if the question becomes, is anything stronger than n to the n? Not that I know of. So I think that's the strongest form you're going to see on any test. So thank you all for watching. I hope this helped. Have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.